In this final video, I have just some comments about RSA. So first of all, encryption and decryption can be more efficient if the exponents are small, but then the question is, how small can they be, right? As you saw in the previous video, when we were going through the mechanics, you were probably nodding off a little bit because it is a lot of number crunching. So where's the balance? When does it become more too easy to factor and to solve this, so that if you publish N and E, a bystander could easily break the messages that you're using, but then you also need to balance that with computation time, because even though it might be easy for you, it could still take you, 5, 10, 50 minutes or 5 hours to break this thing, even with the key, right? If you are working with something, that is 10 to the 50 digits, that could still take up a lot of time. So where's the balance? Well, I'm going to ask this as a quiz question, but what I want you to do is think about the conditions given in there. So if we want, is there a trade-off? Okay, so this is my question. Is there a trade-off on having E small or D small? And what I mean by this is, if one is large, does that mean the other is small or not? I don't know. I want you to do some thinking. Okay, and the other thing is, what is kind of a lower bound? Okay, so what is a lower bound for E, and maybe even for D? Okay, so look for those in a quiz. Okay, having completed the quiz, you'll see the answer in there. Okay, but the next question I want to tackle is, how secure is RSA? So again, you're publishing almost everything related to this cipher. The only thing that you're not publishing is the message, right? If you know capital N, then okay, again, N would factor as PQ. Okay, so you would know N, but you may not know these P, or the P and the Q. But the trick to this would be, if you want to decrypt it, you need to know this D value, right? So then therefore you need to know P minus 1, Q minus 1. Okay, and so this next question is, how easy is it to factor N? Well, let's look at this from a slightly different angle. Okay, let's say I want to know this eventually. Now I'm just going to do some algebra. What is this algebraically? Well, this is PQ minus P minus Q plus 1, right? Okay, well, that's really just saying N and then minus P plus Q and then plus 1, right? Okay, so we already know N, right? That's given to us. Okay, so we just need to know what P plus Q and then add 1 to it to figure out what this P minus 1, Q minus 1 is, and then we would have our factorization, right? Okay, well, this equation here almost has like a quadratic form idea to it, right? What we could think of this as, or we could compare this sort of equation to if we had like x squared and then minus P plus Q times x, so we would add that, and then we would have PQ here, right? And if we were to factor this, so again, we could replace 1 with x, and that would be just fine. But then this would factor as x minus P and x minus Q, and you could use the quadratic formula to find the roots of this, right? So you could set it equal to 0 and solve, and then we would have the values of P and Q. But now again, this is assuming Eve knows, or an eavesdropper would know the value of P plus Q. If they don't know what P plus Q add up to, then it really isn't it will actually require about the same amount of work for the Eve or any bystander to figure out what P plus Q add up to and solve this problem, as it is just to find the brute force factorization of n, to find p and q on their own. So it ends up being about a time sink either way, or same amount, or requiring the same amount of time either way. Okay, so all said, how secure is it? Well, it's good until n becomes easy to factor. That's really the key point. Okay, when n becomes difficult to factor, that's when it's probably a pretty good enough problem for right now. Okay, so generally think of something like 10 to the at least. So the number of digits is at least 10 to the 30th. Okay, which that's a good problem to solve. Okay, and your next homework assignment. Just kidding. Anyway, the last thing I wanted to mention is that in section 3.3, and this is really the only thing that I'm going to talk about from 3.3, is the man in the middle attack that is described there. And this, I don't know why this would ever happen, but somehow Alice and Bob are sending each other messages, and somehow Eve, of course, tricky Eve. Okay, so Eve is right smack dab in the middle of their communication, and so Alice and Bob are trying to send messages to each other, right? But all the messages are going directly through Eve without them knowing, and that's where this is a little hard to believe, at least in today's society. But anyway, so all the messages are going between Alice and Bob are being filtered through Eve, and so what is actually happening is not this so much as Alice is sending a message to Eve, and that is encrypted. So if we just think generally about public key cryptography, so there's A being sent to Eve, roughly. So this is roughly following the RSA encryption algorithm, and then what Eve is doing is she is sending a different message. So she's sending E to Bob, and this is computed as E to the C, E to the E, where the keys are slightly different. Okay, so she's using a different encryption exponent in comparison to Bob, but Bob doesn't know anything else. Okay, he doesn't know that it's being filtered. And then similarly, when Bob is sending messages, so he's sending B, which is computed as E to the B, his own private key. Eve is again intercepting it and reading the messages and then resending it out as a different message as E to the GE. Okay, so the messages, the G isn't changing between Alice and Bob, but Eve is able to decrypt the message as she receives it and then encrypt it back to Bob, and Bob is still able, or Alice or Bob really, are able to read the message not having known that Eve has already read it. So this is kind of the optimal attack that you could apply in this scenario, but this also means that Eve has to have substantial knowledge, or she has to have what they call as an oracle, or an RSA oracle, to be able to decipher all this quickly. Realistically, not something that would happen in society, but nevertheless, that's the highlight of that section, and a vulnerability to RSA nonetheless. Alright, so that's going to wrap up our instruction for RSA, and really the semester. Okay, so we'll see you in class soon.